when we train a graph neural network for the purposes of graph classification as opposed to node classification, many of the steps remain the same, but there are a few differences. The first thing is you generate embeddings for each node using the usual message passing techniques. So you perform multiple rounds of message passing. That is, you aggregate information from the neighboring nodes for every node in the graph. Once you have the updated node embeddings for every node in the graph, you aggregate node embeddings across the entire graph structure into a unified graph embedding. This is referred to as the readout layer. Once you have one graph embedding representing the entire graph, you pass that through a linear classifier to categorize or classify that particular graph. Let's set up a graph neural network to perform exactly these three steps. This neural network class is called GCN. So it's a convolutional network because we still use message passing and aggregation. That is, we still use graph convolution. The init method only takes in the hidden channels, and we set up 3 GCN convolutional layers. The first layer, conv1, has input channels equal to the number of node features, which we know is 3 for our graph dataset. The number of hidden units in all 3 layers is equal to the hidden channels parameter that we specify. Now, the fact that we are using the GCN conv layer here in this model means that we are using message passing and local neighborhood structure information in order to update the embeddings for each node in the graphs. In addition, this GCN conv layer performs something called neighborhood normalization, which typically involves averaging or normalizing the features of a node's neighbors before combining them with the node's own features. Just keep this in mind because this will become important when we come to an alternative architecture that we can use for this graph classification model. In addition, through the graph convolutional layers, our neural network has a linear layer that acts as a classifier, classifying the graphs into one of 2 categories, enzyme or non-enzyme. Here is what the forward pass through the graph neural network looks like. The code on lines 22 through 26 is responsible for generating node embeddings using the local neighborhood information using message passing. We pass the X features of the nodes in the graph, along with the connections of the graph, the edge index, through the first convolutional layer. We use a ReLU activation and then pass that through second convolutional layer with the ReLU activation and pass the output through the third convolutional layers. The fact that we have 3 convolutional layers means that for each node, the node information from 3 hops away will be aggregated and used to update the embeddings for that node. So the local neighborhood from 3 hops away will be considered. Once we have the embeddings for all of the individual nodes in the graph, we need to aggregate these node embeddings into a unified single embedding for the graph as a whole. This is done using the readout layer. You can use different readout layers for aggregation, but the most common one is to simply take the average of all of the node embeddings for a graph, and this is done using the global mean pool function in PyTorch geometric. The global mean pool takes in the node embeddings of all nodes in the mini batch that we've passed in through this forward pass, and it also uses the assignment vector in the batch variable to compute a graph embedding for every graph in the batch. The output of global mean pool will be batch size, hidden channels. That is, we'll have an embedding representation for every graph that's present in the batch. We then pass these batched graph embeddings through a dropout layer on line 33 using a dropout of 50%, and then finally, we pass these embeddings through a linear classifier on line 34. This linear classifier is what will give us our final classification prediction. Now that we have our graph neural network for graph classification, let's go ahead and instantiate the model and move it to the CUDA device that I have enabled for training. I'm using 64 hidden channels to represent the embeddings of the graph nodes. Let's take a look at the total number of parameters that will be trained for this model, and you can see it's 8,706. You can also see our model with the 3 graph convolutional layers and the final linear layer.